Okay, welcome to the second half of Unit 4. So in the first half we talked about probability, likelihood, types of probability, and it was a lot of drawing of our sample spaces, creating of representation such as a two-way table, a Venn diagram, or a probability tree diagram, and then utilizing this visual to help us manipulate our formulas for the different situations. So basically we were looking at the situation at hand, and then we were finding the math behind it. Well, now we're looking at random variables, and still very similar to probability. This is just special types of probability. And so, for example, we have some definitions here that are going to help us interpret some of the things from this unit. So the first one being that a probability model, so a probability model, this describes the the possible outcomes of a chance process and the likelihood that those outcomes will occur. This is what we call a probability model. Something that takes numerical values that describe the outcomes of some chance process, as previously stated. This is what we call a random variable. And what gives the possible values and their probabilities for a random variable is what we call a probability distribution. And so I'm going to abbreviate probability as P-prob, and then random variable as RV. Oh my gosh, I tragically cannot draw arrows. Okay, and you can't even see it, perfect. All right, well, we have special types of random variables. For example, a random variable where x takes a fixed set of possible values with possible gaps between. This is what we call a discrete random variable. And where a random variable where x takes on all values in an interval of numbers, this is what we call a continuous random variable. So two types of random variables. Discrete, which is the countable ones, such as the number of siblings, the number of heads or tails in a coin, the sum of your two dice rolls, etc. Those are discrete values. There's gaps in between, right? There's not a 1.5 sibling, there's not a 1.5 sum on the two rolls of dice. And then the other one, which is the continuous random variables, this is things like height, weight, etc. And we did some work with continuous random variables back with the normal distribution. So we're just building upon what we already know. Okay, so let's take a look here at some possible some examples. So, consider flipping a fair coin 3 times to find x as the number of heads obtained. Okay, and so list the sample space. Remember, we're going to list the sample space as so to indicate the relation. This is just a notorious one. So I'm actually going to start by doing this. So my first flip, I can get heads or tails. And then in my second flip, I can get heads or tails for either or, given that the first was a heads or a tails. And then in my third flip, again, I can get heads or tails for each of these flips here. All right, and the reason I do this tree diagram, it just helps me list out my sample space, because if I list it off the top of my head, I guarantee I'm going to miss a few. So now this makes it very easy. For example, my first pathway is heads, heads, heads. So that goes first into the sample space. Then my second pathway is heads, heads, tails. My third pathway would be heads, tails, heads. Fourth pathway would be heads, tails, tails. So 1, 2, 3, 4. Fifth pathway would be tails, heads, heads. Sixth would be tails, heads, tails. Seventh would be tails, tails, heads. And then eighth would be tails, tails, tails. And that is my sample space for flipping a fair coin 3 times. And another cool thing about this is notice there are 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes here. Well, on my first flip, there's 2 possible outcomes. On the second flip, there are another 2 possible outcomes, and then on the third flip, there are another 2. So 2 times 2 times 2 gives us 8 possible events in our sample space here. So looking at these 8, we are counting the number of heads obtained. So I look, and I can have up to 3 heads, or I can have no heads. And then in some of the other variations, there's 1 or 2 heads. Next up, I know that in each of these events, there is 8 outcomes for this total sample space. So the number of ways I can get 0 heads, I look, there's only 1 way. In the same way, the only way I can get all 3 heads is 1 way. Then we look for 1 heads. Okay, it's going to be 1, 2, 3. And then either by the complement rule or by counting, the number of ways I get 2 heads would also be 3. So the probability of getting 0 heads, if I tossed a fair coin 3 times, would be 1/8, and so forth. And that's how we rate these probabilities. So let's create a histogram of the table above. Now normally we are used to histograms being the intervals in between, because there are possible values that lie in between. But for discrete random variables, we're actually changing this up a little bit. So I'm going to have a scale here. So I'm going to do half, 1. And these tick marks in the middle don't represent like 1.5 or 2.5. They're just how I'm going to treat my bar diagram. So this x variable here is the number of heads. Sorry, the x-axis. And the y-axis is going to be my relative frequencies for each. So I can have 0 eighths, I can have 1/8, I can have 2/8, or 3/8, all the way up to 4/8, but that would not be valid here in this sense. So let's go ahead and draw in our histogram. So for the first one, for 0, I've got 1/8. For 1, I've got 3/8, so I'll put that up there, and same for 2. Those will both be 3/8. And again, I put these tick marks too to kind of space myself out, because we know in a histogram, each of the bars are of equal width. And then lastly, for 3 here, I would get 1/8 as well. And so now, just looking at this histogram, right, it says describe the distribution. So looking at this histogram, well, I see a range here. So I have a range of 3 heads, right? A range or variation of 3 heads, since that is the difference between 3, which is the maximum number of heads, and 0, which is the minimum number of heads. Or technically the minimum is 1. Okay, that gets weird. But basically, the x values can be 3 or 0. So I have a range of 3 heads. Looking at the shape of my data, the shape appears approximately symmetric, or what we could call bimodal here, since there's 2 peaks, and that'll actually lead us into our next unusual feature. So we have peaks at 1 and 2 heads. Okay, and then I'll even put bimodal here in parentheses, because I know my students will chastise me if I don't, and then they'll ask me all of these questions, etc. We're covered because we said approximately symmetric, but yes, specifically this is a bimodal distribution. And lastly, we need a measure of center. So we could technically find the mean, but we've typically described distributions using the median. So the median will occur at blank number of heads. Well, remember, good old median formula. So the median equals n plus 1 over 2. And here we have 8 observations. And so that'll give us 4.5. So the median occurs between the 4th and 5th observation. So we go, this is the first, the third, 3, 1. So since it happens between the 4th and the 5th, the median would be here at 2 heads. So it's just a bit of a blast from the past in describing the data, creating our graphical display. And then the new information here is taking the sample space, which we learned about at the first half of the unit, and creating our random variable. And now from this point in the process, I could ask you, what is the probability of obtaining 1 head? What is the probability of obtaining at least 1 head? What is the probability of not obtaining 2 heads? etc. So we can apply each of our probability rules to this distribution now that we have it defined.